Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process from Max Planck, who was one of the greatest scientists in this last century. We have no right to assume that any physical laws exist, or if they have existed up to now, that they will continue to exist in a similar manner. In other words, what he is stating that everything is subjected to scrutiny and change if it's found to be wrong. So one should not use the laws as a gospel of Bible, rather you should question its wisdom. And if you recall that in the last lecture we discussed about basically the solid propellant rocket engine, liquid propellant rocket engines, and hybrid propellant rocket engines, and their various components in a broad sense. And then we also looked at the advantages and disadvantages over the others. And in the end we looked at the various applications of the rocket engines, and you will be surprised to know that it's having a large number of applications that what common sense says to us. And as I told in the last lecture, that it depends on the people's imagination and the requirements by which they can find out various applications of rocket engine, not only for the civilian even, for civilian application even. Today we will be discussing about fundamentals of aerothermodynamics, and all of you know that what we will be discussing, but we will be just looking at recalling some of the aspects so that it will be useful for us to understand the aerothermodynamics involved in rocket engine. But today in this lecture we will be just looking at the rudimentary elements of the aerothermodynamics. When you say that fluid is always there, that means the certain things are moving in certain direction, that we call it as a fluid flow. Fluid flow is a part of life around it, and we use it for rocket engine profusely, both the gaseous fuel and the liquid fuels and liquid propellants and gaseous propellant, liquid propellant, and also the can be utilized for producing the thrust in rocket engines. The fluid flow can be classified in various ways. Could you please recall what are the ways we can classify? Of course, we can classify into steady and unsteady flow. That means if the flow properties, pressure or temperature or the velocity is not changing with respect to time, we call it as a steady flow. And if the flow properties are changing with respect to time, we call unsteady flows. And of course, the steady flow, which is easier to handle, unsteady is not that easy, but some of the flows are unsteady in nature. And beside this, based on the viscosity, we can say viscous flow or inviscid flow. And of course, inviscid flow is easier to handle, that we will be dealing with in our analysis. And viscous flow, you cannot be ruled out as long as the fluid is moving over the surface of the solid and others. It will definitely having the viscous regions, as you will see. Let us to discuss that further. Let us that flows in which frictional effects are significant, that we call it as a viscous flow. And inviscid flow, particularly in rocket engine, viscous forces are negligibly small, inviscid flow where the frictional effects can be neglected very easily. Keep in mind that in a rocket engine, viscous forces are negligibly small as compared to the inertial or pressure forces in region away from the wall region. To illustrate this point, let us look at a flat plate over here. In this case, the if you look at this, a uniform velocity profile, right, and this flow we can call it as a uniform flow. You can produce that in a laboratory, not in a otherwise using various honeycombs and other devices. If the flow is coming over a flat plate, this is your flat plate, then what will happen? This is a solid surface, and as we are assuming the continuum over a flat plate with a uniform velocity which I have shown here, and if you look at the, this is let us say x direction and this is let us say y direction over the plate, and when the fluid is passing over the plate and the fluid elements which will be really there in this plate moving along with the x direction, it will be resisted by the plate because of fact that the fluid cannot enter into here, and then fluid element will be sticking to the plate due to inertia because of fact that this plate is basically is fixed, and due to continuum the velocity along the x direction will be 0 at any point on the surface of the plate, and also the wall of this plate, both the velocity along the x direction, y direction will be. As a result, what will happen, this the fluid elements will be getting dragged and then it will be resisted, and there is a viscous force which will be acting over here. As a result, the velocity will be 0 at this point, and then it will be increasing, and then of course it will reach a free stream values and resulting a velocity profile. So, if you look at this, is basically we can call it as a uniform flow, and this is a non-uniform flow, and this is coming in because of fact that in this region you can say that this region will be viscous region as shown here. This is your viscous region, and this is your inviscid region. This region is inviscid flow region. So, therefore, it is really very difficult to avoid the viscous region. However, due to as it is very small and confined to the wall, particularly at a high velocity or high Reynolds number, then we can analyze it without really considering the viscous region having much effect on the process. So, that will be inviscid flow region. And the flow can be rotational and irrotational. If you look at the fluid element, if I consider this as a boundary layer, then the fluid element will be rotating here. Like if you look at this fluid element will be rotating, and that is in this region there will be rotational flow. But in the inviscid region, in this region, the fluid element, if it is the element here like this, and it will be remaining as same without any rotational. This is basically irrotational flow. In this region, if you consider this is basically irrotational flow region. So, and also depending on the Reynolds number or whether the laminar, it can be divided two categories. One is laminar and turbulent flow, which will be judged by the Reynolds number, and laminar flow means is basically flow will be layer by layer, it won't be really transport in the transverse direction, and whereas the turbulent will be three dimensional in nature. and flow can be compressible and incompressible. Compressible, the density changes will be much higher. Incompressible flow, generally density change of the flow when it is moving, it won't be there or negligibly small. And most of the liquid, when it flows, it is generally considered as an incompressible fluid, and the air, when it is moving or the gas is moving at a lower velocity, we call it, can be considered as an incompressible fluid, but at a very high velocity it is considered as a compressible flow. And in a rocket engine, we will be using both the liquid and gaseous, and then both incompressible and compressible fluid will be using. Besides this, flow can be divided based on the dimension, one dimensional, two dimensional and three dimensional flow. As I told earlier, that if it is a uniform, that means the flow is here in only remaining constant along this direction, right, along the r directions, and it is changing in the one direction, that we call it one dimensional, and when the flow will be changing in both direction, we call two dimensional, and of course the flow will be three dimensional. Let us look at it further. That flow field is best characterized by its velocity distribution. Flow is said to be one dimensional, two dimensional, three dimensional if the flow velocity varies in 1, 2 or 3 directions or the dimensions respectively, then we call it as let us look at a tube flow, and which is having a diverging section. This is your basically divergent sections, and this is a tube, you can say, and if this tube is basically is coming as a very longer tube, and it is coming from earlier, let us say, and if I am having a uniform velocity profile to start with, then we call it as a basically it will be changing, it will be taking some parabolic shape, and this shape will be changing, and as a result the flow in the, if I say this is the basically x direction, and this is your center line, and this is your radial directions, then it will be changing both along with the x directions and also the radial direction. We call it as a two dimensional flow, but here in the beginning this will be one dimensional flow, and generally one dimensional flow will not be existing in the nature. You will have to make it by using proper devices like your honeycomb and tube bundles and other things. And once it is fully developed, of course this velocity profile won't be changing much, and it will be only varying in the r directions, not in the x direction when it is fully developed flow. And of course when it goes in the divergence section, then there will be change in the velocity, and it will be changing in the both the x direction and r direction. So then flow becomes two dimensional again. So let us look at the flow over a spacecraft, which is showing these are the streamlines. You can see the flow is three dimensional in nature. In nature, generally the flow will be three dimensional. However, for our analysis, we will be assuming it to be axisymmetric or two dimensional kind of thing to make a thing, and we can also produce two dimensional flow in laboratory and also in certain devices. However, the variation of velocity in certain direction can be small related to variation in other direction, and hence can be ignored in and considered is to be either two dimensional flow or one dimensional flow. Inherently flow is three dimensional. So now having talked about little bit about the fluid flow, we will be discussing about the thermodynamics. A question might be coming in your mind, what is thermodynamics, or what do you mean by thermodynamics? If you look at thermodynamics, is basically stems from a Greek word that is thermo and dynamics. Thermo means is basically heat, and dynamics means is the power. So therefore, when you talk about that, it's basically heat and its interaction in producing certain power or work, what we call dynamics means power. So therefore, and when the classical thermodynamics we are talking about, you are basically talking about the in equilibrium state. Therefore, when you are talking about the thermodynamics, we talk about energy and equilibrium and entropy. That is the classical thermodynamics what we will be dealing with. We will be not dealing with the statistical thermodynamics, because it will be dealing with the macroscopic effects of the changes that is occurred due to the interaction of heat and work. And you can say this is the basically triangle of thermodynamics that you keep in mind. And is it related to the human life or the life? As a matter of fact, let us look at, if you look at life, it will be having body and it will be having mind, and the spirit which is making all this thing to happen, or any actions or interactions, that is the spirit. So you can see that it is life triangle, and that on the right hand side, on the left hand side is thermodynamic triangle. A question might be arises, is it really can be interlinked? That question I am leaving to you. You can see that lot of similarities between that, because if you want to lead a good life, you will have to taking care of the spirit, and while the body and mind can interact with each other and do the work. That means you will have to keep in equilibrium, and that is true in the thermodynamics, and always in trying to equilibrium, to maintain the equilibrium, the action takes place, and there will be change in the entropy and change in the energy and interaction will be going on. So this thermodynamics is basically governed by certain basic principles, and those are we are aware. And if you recall, thermodynamics is a science dealing with the energy and its transformation. We know very well that according to the first law of thermodynamics, for an isolated system, energy can neither be created, it can be destroyed, it can be converted into one form into another. So that is we know, and energy is having interaction with the system and surroundings, and as a result there will be some work done, and then there will be also a change of heat transfer that which will be taking place between system and surrounding. So energy is an enticing entity that governs all the activities of the entire cosmos. Therefore, it is everywhere, not only in the rocket engine, but in the all devices, including human body, animals, and cosmos, and other things. So therefore, thermodynamics plays a very important role for understanding any system, as a matter of fact. So therefore, and when you talk about that, then you will be trying to maintain the equilibrium, and equilibrium process is basically governed by second and the 0th law of thermodynamics. 0th law, all of you know, that is talking about thermal equilibrium, right, process. And you might be aware that whenever you use the thermometer, we keep with the body for measuring its temperature for a longer period, so that equilibrium is maintained, so that you can get the temperature being registered in your thermometer, and which is equivalent to that of the body. So and the entropy, which is governed by the 3rd law, and 3rd law thermodynamics basically defines the entropy of a crystalline material at 0 Kelvin. So that is not being used very much. What we will be using in our analysis is the first law of thermodynamics and second law of thermodynamics profusely. All these 4 laws of thermodynamics are based on experimental observation which cannot be proved mathematically and directly. So, and thermodynamics, as I told, is a fascinating subject used in almost all engineering and science branches. Nowadays people are talking of using the concept of entropy in economics and other places as well. So, the first, let us recall what do you mean by first law of thermodynamics, and this law was basically developed by conducting experiment by famous J.P. Joule, and who carried out a series of experiments, and he found out this law based on experimental observation, and that is basically the state that whenever a system undergoes a cyclic change, however the complex the cycle may be, cycle integral of work is equal to the cycle integral of the heat. What is the meaning of that? What it says that this is cyclic integral of dq is proportional to the cyclic integral of work. That is cyclic integral in the basically it is working on a cycle, and that is it states. And then when you write down as I told that this was firstly proposed by great scientist J.P. Joule in 1851 after conducting series of experiment in a very systematic manner. This is basically, if you look at this cycle integral of dq is equal to a constant, this is known as Joule's constant dw, this is Joule constant, and for SI unit J is equal to 1. As a result, dq is equal to cycle integral of dq is equal to the cycle integral of work. This is the first law of thermodynamics, what we state. And what is the meaning? You can say that basically from the system, because if you recall the definition of the system, that where you will be concentrating your attention and then having certain fixed boundary, and dq is basically from the system the heat whatever the being going out and coming in, that is the balance, that is the and dw is from the on the system itself, work is done by the system or in the system is equal to 0. There will be certain sign convention you will have to use. The work done by the system is positive and work done on the system is basically negative, and for heat it is just opposite around. Transfer from the system is negative, work is entering into the system is positive. So, with this sign convention, if you do, you will get this equation, that is you can say equation 1, and this is applicable for the cyclic process only. But however, lot of this thing cannot be used for this, and keep in mind that first law of thermodynamics is generalization of several experimental data produced by J.P. Joule, and as I told earlier around 1851, and till date nobody has disproved this law, but this law cannot be proved like theorems in mathematics. As I told earlier that this law whatever we have discussed, this is I can call it as also 1, this will be valid for the cyclic process, and but for a lot of systems which will practice is a closed system, there will be open system. A closed system is one where there will be interaction. Let us say this is your system, is a kind of a room where there is a heat is transfer, work is going on, that means work is not there, there is no work done. This is your system boundary. So, therefore, this is known as closed system. So, the closed system is one, there will be an energy interaction between the system and its surrounding, however, there won't be any mass interaction. So, for a closed system, dq minus dw is equal to dE, that is the property of the system. And if you look at dE is a energy, the change in energy, and E represents all the stored energy of the system. It consists of internal energy, that is U, and this is the microscopic form of energy which is stored inside the system, whereas the kinetic energy Ke is the kinetic energy and the P is the potential energy, right. Ke is basically kinetic energy which is due to the motion of a system, and then Pe is your potential energy, and these are macroscopic form of energy. You can see that the both together we call it as a the total energy, and that remains will be that is being balanced with the change in the heat interaction between the system and its and also surroundings, so also the work done. What it states is basically change in the heat interaction minus the change in work is equal to total energy of the things. So, this is about the closed system, and we will be discussing in the next lecture about the open system, because in rocket engines the open system is being used. Therefore, in the next lecture we will be discussing about the open system and other laws of thermodynamics, and later on we will be moving into the other aspects of the combustions and other things which will be useful for analyzing the rocket engine. Thank you very much.